Hello students. So, in today's lecture we will continue with some examples on Stokes theorem, and since today is our last lecture, I apologize that I couldn't be able to cover more examples on integral calculus section as I promised or showed you in our syllabus, but I tried to compute as many examples as I could, also because the time is very limited, and because of that sometimes I also had to rush through, and maybe on one or two occasions we couldn't be able to do more examples, but I suggest you to follow any one of the textbooks, or if possible then follow all the textbooks which I suggested in the reference right at the beginning of this course, and I'm pretty sure there you will be able to find a lot of examples just for you to practice and get really good at it. And I am also providing a lot of assignments, so try to solve those assignments. That will definitely help you clear out your doubts, and would also help you to become how to say very good at this particular subject. So, today let us start with our last topic, which is Stokes theorem, and I am going to solve some examples, and let us do that. So, verify Stokes theorem for f equals to 2x minus y times I minus y z square j minus y square z k, where S is the upper half or upper half surface of the sphere and C is its boundary. So, what we have basically is a sphere, and we have to verify the Stokes theorem on the upper half of that sphere. So, that means if you consider, let us say, x axis, y axis and z axis, then we can consider the upper half as from z equals to 0 till z equals to 1. So, that means that could be one upper half, or x equals to 0 till x equals to 1. So, that can be another upper half. So, any on any one of the upper half basically, and in this case to do that, first of all, to verify actually the Stokes theorem, we write the statement. So, by Stokes theorem, what do we have? We have line integral f dot dr equals to surface integral curl of f dot n ds, right. So, we have to, so that left hand side is equal to the right hand side. So, let us start with the left hand side. So, it is line integral f dot dr. So, here C is the boundary in the xy plane, and we are considering basically z equals to 0 part. So, z equals to 0 to z equals to 1, and if C is the boundary, then in xy plane, then it is basically that circle, right. So, that is basically the circle, and if you walk along that circle, then in the anti-clockwise direction, then your surface is falling on the left hand side. So, that makes sense. Let me write one or two lines before I actually calculate this line integral. So, in order to do that, the boundary, so let us write the boundary C of the surface S is the circle in xy plane of radius unity and center origin, and the parametric representation of that circle would be x equals to cos t, y equals to sin t, and z equals to 0. So, now the line integral, and t is basically where t is between 0 to 2 pi. All right. So, now we have line integral f dot dr. So, f is basically 2x dot dr. Dr is basically dxi plus dyj plus dz k. Now, if we take the dot product, then this will be basically two x minus y dx, since z equals to 0 and dz is 0. So, here z will be 0 because on the curve C we have taken z as 0, right. So, on the curve C we have taken z as 0. So, we substitute z equals to 0 here, and we substitute dz equals to also 0. So, ultimately we will get 2 x minus y dot times dx. So, that is what we are obtaining here. And now, we substitute x equals to cos t and y equals to sin t. So, this will be t running from 0 to 2 pi. 2 x means 2 cos t minus sin t dx dt times dt. So, this is t. So, t running from 0 to 2 pi, 2 cos t minus sin t, and x is cos t. So, dx will be minus of sin t. So, I can write the minus sign here, sin t dt, and then we multiply this sin t here. So, this will be 2 sin t cos t. So, that means sin 2 t, and then we will have a minus minus plus 2 sin square t, which can be written as, this is dt. So, which can be written as 1 minus cos 2 t. So, that is cos and sin formula we have to remember, and then you substitute the value, then you substitute those calculations here. So, this will be t running from 0 to 2 pi. We have sin 2 t minus half 1 minus cos 2 t. So, we just adjust a 2 here dt, and then we integrate term by term, and ultimately we will obtain pi, right. So, ultimately we will obtain pi. Now, we calculate the right hand side. So, first of all we have to calculate curl of f. So, this we have I, j, k, and f would be 2 x minus y minus of y z square minus of y square z. So, when we do the partial derivative, we will ultimately obtain a k, because rest of the term will be either cancelled out or they will either be 0. So, they do not play any role, and therefore, the component of I j and k will be I j will be 0 and k will be 1. So, that is why we are only writing the vector unit vector k, and n is the unit outward drawn normal on the surface S. So, if C is the curve basically that is enclosing that surface, and if n is the outward drawn normal. So, you have a sphere on the upper half of the z axis, and then if you have a unit drawn normal n, then you can choose k axis itself as your unit normal, right, because k axis is normal to that surface of the sphere, and we can actually choose it. Instead of calculating, we can actually choose k as the unit vector, and therefore, we can write if S1 is the plane region bounded by the circle C, then so basically we have this as surface integral over S1. Let us say we have gradient of curl of f dot n is basically k, and now this thing is also k. So, k dot k ds, therefore, k dot k is 1, this will be surface integral over S k square, and since k is the unit vector, we can write k dot k as 1. So, this is basically ds and surface integral over S1, and this can be written as ds pi r square, r is 1. So, then we have basically pi. So, our left hand side was pi and our right hand side is also pi. Therefore, if the left hand side and right hand side are both same, then by Stokes theorem we can be able to say that the given integral or the given problem satisfies the Stokes theorem, which means that the surface integral and the line integral both are same or both hold true. All right. So, that is one way we can solve our problems in Stokes theorem, motivated from Stokes theorem. Similarly, you can have several other problems from Stokes theorem, where you either convert your surface integral into a line integral, or you can convert your line integral into a surface integral, and just calculate either one of them. So, if one expression is given to be complicated, try to use the Stokes theorem to convert it into a simpler one, and see if you can calculate that one or not. All right. So, let me give you a quick recap of the syllabus. So, before I proceed any further, so we started. Initially we started this integral and vector calculus course from Riemann integral, or from the concepts of Riemann integral. So, I know that in your plus 2 or even when you were preparing for other competitive exams, you must have learnt a little bit about indefinite integral, then definite integral. Those are all very nice form of integrals, or sometimes they are also called as Newtonian integral. So, where you look for the antiderivative, and you either by method of substitution or whatever methods are unknown, you just use them to calculate the integral. So, more or less, since you were familiar with the integral of a function or integral of single variable, we started with concepts of Riemann integral. I gave you introduction of partition concepts of Riemann integral, Riemann integrable function, fundamental theorem of integral calculus, mean value theorems, and things like that, and based on which we will also provide you some examples or assignments to practice. Then we looked into reduction formula and derivation of different types of reduction formula. So, sometimes you may be asked to calculate sine to the power 13 x dx. So, then in that case you just have to use that reduction formula for sine to the power n x dx, and from that formula you can be able to calculate whatever power is given there. So, the reduction formula is a very nice tool where you just see if there is some kind of repetitive formula there, so that you can come to a generalized formula. And then we learnt about improper and proper and improper integral, their convergence. We also learnt about some tests to do the convergence. All right. And afterwards we moved to beta and gamma function. We looked into their properties. We learnt about differentiation under the integral sign, Leibniz theorem, and things like that. Afterwards We looked into double integral. We also learned about change of order of integration, Jacobian transformation. Then we moved to the applied part of integral calculus, where we learnt about rectification and surface integral. We learnt about volume integrals, and several other types of volume integrals. The center of gravity and moment of inertia, I did not cover that part because from integral calculus perspective, I think it might go a little bit in the different direction. So, if any one of you are interested, you can look into those references. Since I was focused to also cover the vector calculus part, I gave my attention to those two topics. So, these are the two topics which I initially proposed, but then over the time I realized that this might lead to problems from different parts of mechanics or something. So, it is better that we should not do it at the moment, but if any one of you are interested, you should just look into those books and you will be able to find these two topics there. And then we moved to our vector calculus part, where we looked into the limit, continuity, differentiability of a vector function, arc length, partial derivative of vector function, directional derivative, gradient, divergence and curl operators. So, we learned about different types of notions in vector calculus. We also practiced some examples. Then we learnt about tangent, normal and binormal, and then we derived one of the important formulas in vector calculus, which is the Serret-Frenet formula. We also looked into the applied part of vector calculus, where it is used and how to derive some equations of motions and things like that. We then looked into three important theorems like Gauss divergence theorem, Stokes theorem and Green's theorem. So, up until previous class, I did try to cover Green's theorem, Gauss theorem, and today we learnt about Stokes theorem. We also tried to solve one example motivated from the Stokes theorem. And in our 12th week, or in our last week, I thought maybe I could practice more examples from integral calculus or vector calculus, but due to the time constraint, unfortunately we cannot be able to practice more examples, but I would suggest you to look into those books. There you will find plenty of examples for you to practice and work out problems from our assignment sheet. That will also help you get a sense of this topic. And this is what we tried to cover in a 12-week session actually, although I personally feel that it might need a little bit more time to cover these two topics in detail. However, we tried our best to do that. So, just go through these lectures and try to get a sense, a feeling of the topic, whatever we learned and talked about. And if you have any questions or doubts, I believe we have a weekly sessions where we can clear out the doubts. Also, if you have any questions, you can just go into my homepage and write me an email. I will be more than happy to answer your questions and try to help you with your queries. So, you don't have to just worry about the things. You don't have to just worry about the fact that you can only contact me via this NPTEL format or something. So, if you have any in general any questions or doubts on integral calculus or vector calculus, or which you couldn't be able to follow in this lecture series, then just write me an email. Go to the IIT Kharagpur website, try to find out my profile. There you find my email address and write me an email, and I will be more than happy to answer your queries. So, from my side, I try to cover as many topics as I could, and I hope you'll be able to learn these things more clearly, and I look forward to your questions, your queries, and yeah, good luck. Since we still have at least 5 minutes left, so let me just state one more example from Stokes theorem, and then we'll move. I will close this lecture. So, let me go back to my. All right. So, since we have one more some time, we can focus on one more example. So, example 2 from Stokes theorem. So, verify Stokes theorem. f is equals to x square plus y square times I minus 2 x y j taken around the rectangle bounded by x equals to plus minus a and y equals to 0 and y equals to b. So, this is just one more example for us to practice. It is really not that much complicated. It is a lengthy problem, but it is really not complicated. So, if we want to draw this this rectangle, we can just do that x equals to minus a, x equals to a, and this is our x axis, this is our y axis, and then we have y equals to 0 and we have y equals to b. Sorry. So, this is our x equals to a, and our rectangle, this is our rectangle. So, our curve C will move like this. So, this is our curve C, all right, and the equation of this line is x equals to a, this line is y equals to b, this line is y equals to 0, and this is x equals to minus a. So, these are the 4 equations, and let us call it as a, b, c and d. So, first of all, in order to verify, we have to calculate the surface integral, and the surface integral can be calculated by, so we first need to calculate curl of f. So, curl of f can be calculated using that determinant form, which is basically I, j and k, and then we have del del x, del del y and del del z, and we can write the x component x square plus y square, y component 2 x y, and then z component is 0. If you calculate this determinant, then ultimately you will be able to obtain minus 4 y k. And a unit normal, since this whole curve this whole surface lies in the x y plane, an outward drawn unit normal would be n equals to k, all right, because z axis is obviously perpendicular to the x y plane, and you can choose n as k. So, we choose, or we have, or we get n equals to k, since the given surface is in x y plane. So, therefore, if we want to calculate the surface integral curl of f dot n ds. So, curl of f is basically our minus of 4 y k dot product with k ds, and this is basically minus of 4 y. So, this is basically minus of 4 y ds, and ds is that surface element in x y plane. So, this can be written as minus of 4 surface integral x. So, x is varying from minus a to plus a, and y is varying from 0 to b. Y ds is basically dx dy, and if we integrate this whole thing, then in that case we first integrate with respect to y. So, this will be minus of 4 times b square by 2, and then we integrate with respect to x. So, this will be so this will be 2 a y. So, this will be ultimately 2 a. So, that means we will have minus of 4 a b square. So, that is the value of the surface integral. Now, for the line integral, c, here we have to be a little bit careful, because our curve is composed of 4 curves. Our curve C is composed of 4 mini curves. So, this is our C1, this is our C2, this is our C3, and this is our C4. So, that means we can write this integral over C as the union of C1, C2, C3, C4, and union of C1, C2, C3, C4 can be written as sum of integrals on C1 plus C2 plus C3 plus C4. So, we can write C1 f dot dr plus C2 f dot dr plus C3 f dot dr plus C4 f dot dr. So, we have to evaluate all of these 4 integrals, right. So, when you first evaluate over C1, you have to take care of the fact that the equation on C1 we have y equals to 0, then dy is 0, and you just integrate from minus a to plus a. So, that will be the value on C1. Similarly, when you are integrating on C2, you have to take x equals to a and y is varying from 0 to b. So, so dx will be 0, x is a. So, we calculate the second integral. Similarly, we calculate third and fourth, then you sum all of them and you will be able to see that the required answer is minus 4 ab square, and therefore, your Stokes theorem will be verified. So, this was one more example where you could be able to verify the Stokes theorem. So, I hope these examples have cleared out your doubts based on Stokes theorem, and I believe we have exhausted the time. So, I will stop here for now, and I hope you enjoyed this course, and I will look forward to your questions, your suggestions, your remarks if you have anything based on this course, and I will try to answer them. I will try to reply to you as soon as possible, and of course, I am always reachable via email. So, do not hesitate to contact me. So, thank you for your attention, and have a good time.